Now look at two important properties and get some clarifications on that. The first is pressure. Here we denote this by the symbol P, and the SI units, you can say Pascal, kilopascal, bar, megapascal. So this is 10 to the power 3 Pascal, 10 to the power 5 Pascal, 10 to the power 6 Pascal. And everything that you have come across as pressure so far in your life, that pressure we always assumed implicitly to be an absolute pressure. But what we measure in real life with any instrument is that here is an instrument and here is a system connected whose pressure we want to know. Inside this, we would have the absolute pressure. Outside, we have the ambient pressure. And what this instrument will always end up measuring and giving a signal or an indication is the difference of these two. So P inside minus P ambient is what the instrument tells us. So when you go to the petrol pump to fill air into your tire, and that person does it and shows it that it is 1.2 kg per square centimeter, that is the pressure which is the difference between the actual pressure in the tire, the absolute pressure in the tire, minus the ambient pressure. So what we do is we define this as a gauge pressure, and we say that if the tire pressure there was say 2 bar and ambient pressure is say 1 bar, or say let's take this as 3, then the gauge shows 2 bar. And to tell somebody what the pressure in the tire was, if we say the tire pressure was 2 bar, it means that the absolute pressure in the tire was 2 bar. So if you want to tell them what the pressure was measured, you must always add the symbol G after that. So the tire pressure, whatever is told to us by the manufacturer and what we fill up at the wherever we go, we are always saying that what has been indicated by the manufacturer of the tire is a gauge pressure, and what the chap is filling into your tire is also gauge pressure. And that's why the two have got to be the same. And I'm talking of the thing about the tire, just to tell you that while thermodynamics has its own implications for the car design, whether it is a IC engine car or a hybrid car or whatever, the biggest problem for inefficiency in a vehicle is that we do not maintain proper tire pressure. More pressure than what is the recommended pressure or less pressure than that. In both cases, you will burn more fuel. Simple as that. And the difference can be something like 7 to 10%. It's not small. But back here, this is a gauge pressure, and we always write bar gauge. And if there is no G, it always means it is an absolute pressure. So if I say 5 bar, it is the 5 bar is an absolute pressure. If a gauge pressure is given and we want to know the absolute pressure, then we go back here and that P is equal to P gauge plus P ambient. And say, look, I know what is the gauge pressure. How do I know what is the ambient pressure? So if in the problem it is specified, you take that value. So somebody says the gauge pressure is 751 millimeters of mercury. You take that, and to make it into an SI unit, we multiply this by the density of mercury into 9.81. And this will tell us what is the pressure in. I'm writing the units everywhere because quite often you will see getting mixed up. So somewhere people will report Pascal, somewhere people will report millibar, somewhere we work with megapascal. The units have to be taken care of at every step. So if it is specified, we calculate in Pascal, add it, that's done. If nothing is given, no information, we assume that the ambient pressure is 760 millimeters of mercury. And then we do the same calculation and see how many Pascal that is. And in some cases, if you are told what is the altitude at which it is working, then you can find out that at that altitude, what is the pressure. So for instance, you go to 7,000 meters above mean sea level, the ambient pressure is almost half bar. And that's why I say that breathing becomes a big problem because of lack of oxygen. So we go there and get this value. And in the real world, the best thing is measure it. A very simple measurement. These days many instruments are there. Measure it and see what is the ambient pressure and use that in the calculation. So this is one aspect of this. The second thing that could happen with pressure is if this pressure, instead of being 3 bar, it could have been, say, 7 kilopascal. When I say 7 kilopascal, that's an absolute pressure. And we know that ambient pressure, if I take 760 millimeters of mercury, it's 101.3 kilopascal. So the gauge that is there at the petrol pump cannot measure this pressure. We need another instrument which can pick up pressures below atmospheric pressure. And when we read that gauge, you will get a pressure, and in this case it will show 93 kPa, but that is the gauge pressure, and instead of writing G, we write the word vacuum after that. So this is 93 kPa vacuum, or we can say this is, say, 760 instead of 760, they say about 700 millimeters of mercury vacuum. So this is equivalent to saying that the absolute pressure is 60 mm Hg. 93 kPa vacuum, we assume the ambient to be 101.32, then the absolute pressure will be 101.3 minus 93, so much kPa. And so whatever the number comes, the units of that is only kilopascal. Or in this case it is 7.3, so that's it. This is important because there are many applications where we come across such pressures and we exploit it quite extensively. So got to take care in differentiating between absolute pressure and gauge pressure and correctly interpreting it as to what it is. So that's the issue with pressure, and we'll now look at the other important property right now, which is temperature. We'll come back to it when we look at the laws of thermodynamics. For now, we'll only say that the SI system, the temperature scale is in Kelvin. 0 Kelvin, state that has not been ever achieved. The state where there is maximum possible order in the molecules, and anything as you go above temperature, the molecules begin to have more energy, and that energy is quantified for each molecule by its temperature. Okay. So we start from there, and there is no upper limit on Kelvin. Practically, we may use degrees Celsius, and you all know what is the relation between these two, that the temperature in degrees Celsius plus 273.16 tells you the temperature in Kelvin. We'll come back to it when we look at the laws of thermodynamics in more detail. For now, this is good enough. And the reason I brought it up here is that you've already come across these things in school and in some of your other courses. And many of you have used equations like PV is equal to RT and say PV to the power N is constant and things like that. We have not yet started discussion on this. It will come later on. But the point to note here is that this pressure, these are always absolute pressures and not gauge pressures. And in equations like this is always Kelvin. This is, I want us to keep that in mind when we are looking at all the other things that will come up in the later modules and in solving problems. So that is what I wanted to cover about pressure and temperature. And one more thing, and then we will only take questions. We have time for it. Okay, well, I'll just cover this part, then I'll come back to questions. Okay. We started in the first lecture, we defined what was heat and what is work. And we said that when a system, and this is surroundings, if heat transfer takes place from surroundings to the system only because of a temperature difference across the system boundary, this is heat. What we did not talk about is what happens to the surroundings. So we'll complete that by saying that, okay, if I now only look at the surroundings, so heat transferred to the system from the system's perspective, which is what we are trying to analyze. For the system, this is plus Q. Now we remove the system and say, well, this is the surroundings, and energy transfer took place out of the surroundings. And we said that for the surroundings, this is minus Q. So this definition always goes together, that what happens to the system, the opposite happens to the surroundings. And in case it is the other way around, that the system transfers heat to the surroundings, that means the system here is at a higher temperature than the surroundings there. And in this case, system, we said that this is minus Q, and for surroundings, this is plus Q. And we can extend that argument to work also and say that that's the system and we have the surroundings around it. And if you take this as the system bound, this is the system boundary, then if this temperature, if this system does work on the surroundings, then from a system perspective, we said that this is plus W, and as we just saw there, from the surroundings, this will be minus W. Okay, so that is the surroundings, and same W which was there for the system as plus W is minus W for the surroundings. And if you look at the opposite thing, if the surroundings do work on the system, then for the system this is minus W, and for the surroundings this is plus W. Okay, so that's a point to remember. It will come back again when we look at the second law of thermodynamics. The thing is that having defined this in the context of system and surroundings, the effect on the system will be opposite of the effect on the. That's another thing that I wanted to cover up. Okay, so let's now take some questions. Okay, so the question here is, what does it mean absolute zero reference for temperature scale? When we say that the temperature is 0 Kelvin, this is what we call as absolute zero. And it means there can be no temperature less than this. Okay, this is the lowest possible temperature possible. Minus 5 degrees Celsius is possible. Minus 5 Kelvin, not possible. Okay, so that is the meaning of absolute zero. And if I take a corollary and look at pressure, and we ask, is there something called absolute pressure or the pressure zero? Well, if there is nothing in the system, gas or liquid, there is no pressure. So you can say that then there is vacuum. And technically, this means that P is zero. Okay, so there can be no pressure like, say, 800 millimeters mercury vacuum. Such a thing doesn't exist. You cannot go below 760 millimeters of mercury. Okay, the question here is, why we measure pressure in terms of mercury? It is not necessary that we always measure pressure. The question is, why do we always measure pressure in terms of mercury? Not necessary. We could use any fluid. Historically, mercury is the one that has been coming along. Water, absolutely fine, we could use water, but water has a couple of problems. So mercury, what happens, why it is so convenient, is that ambient pressure is 760 mm, and so if you want to measure pressures below atmospheric pressure, very simple thing works. And to measure pressures above atmospheric pressure, we can use a device like a U-tube manometer. And for pressures which are like a few, up to maybe a meter or so, the manometer height will not be too long. So that is possible. But pressures more than that, we then cannot use U-tube manometers. And then expressing pressure in terms of millimeters of mercury is not convenient at all. So that is there. We could use water, and we often use water because now with density here being 13,600 kg per meter cube, water being 1000 kg per meter cube, for the same height, a mercury manometer will measure a larger pressure than water. So if I want to measure smaller changes of pressure, water is the preferred fluid, not mercury. So if I have a pressure difference of 100 millimeters of water, then mercury will very, very small increase in the level, may not even be possible to measure it. So there are places where we do measure water. Water has a problem, it evaporates. That's something you need to worry about and take care of it. Mercury doesn't have that problem. It has the problem that it is a toxic material. So sometimes we do measure and express pressure in millimeters of water column, mmWc. Quite often it is done, and things like a building air conditioning, where the building it is a slightly higher pressure than the surrounding pressure, that pressure difference cannot be measured in millimeters of mercury. The preferred thing is millimeters of water column, or say millibar. And in most applications we do not even use either of them. We used to use a pressure gauge. It is still there, but gradually this is giving way now, and we have almost completely moved to pressure transducers. Pressure transducer is nothing but a diaphragm which experiences ambient pressure on one side and the applied pressure on the other side, and because of its deflection, it generates an electrical signal or a potential difference that is measured, it is calibrated, and that is taken as the pressure. And of course, this is all electronic. Can we apply laws of thermodynamics to vacuum? Well, you need to define a system. and say, well, what is it doing? So the question, I'll try to create a question out of that and say that here is a chamber which has vacuum in it. This is in vacuum, there is nothing in it. And outside is say ambient pressure. And we have to hold the thing in place, otherwise it will go down. But if we let it go, there is a force acting here, there is no force on this side. This is unrestrained movement. It will just go down and completely sit bang on the bottom. There is no work associated with this. We didn't have a process because we did not have a substance over here. The only thing we can look at is what happens to the surroundings or the work done on the piston as it moves, and see that, look, what is it that the surrounding experienced. But vacuum, there is nothing, there cannot be no heat transfer to it, and in this case, as we have seen, there is no work associated with it. So there is nothing that will happen with vacuum. Using microscopic thermodynamics, how do we define temperature? Okay. So we go back to the idea of defining temperature, and at the microscopic level, what is happening is this. In a solid, we have all these atoms or molecules arranged in a certain way. Intermolecular forces are quite strong, but each one of these is vibrating and oscillating around its mean position. So in a solid, the atoms or molecules are not stationary, they are vibrating, and the energy associated with that vibration or rotation is what we assign it as a number related to temperature. When we heat it, the molecule takes more energy and it begins to oscillate faster. So that is what tells us that the temperature has increased. In gases and fluids, all the molecules are moving around in a random way. Each molecule itself has got its energy, and if how much energy it has is directly proportional to its temperature. So more the energy in the molecule, the greater the temperature it will have. So at a microscopic level, these are very tightly connected. At the macroscopic level, what we do, instead of worrying what each one of them is doing, we take all of them, take their average, and say this is the temperature of this material. The same thing we do with gases, and that's what the kinetic theory of gases teaches us. But again, at 0 Kelvin, there will be no energy in the molecules or in the atoms, and so energy becomes 0. And after that, nothing can be done. We take a minute to tell you what is the counterpart of this for pressure. In solids, pressure is not defined. We define only stresses, so we will leave it away. For fluids, we define pressure. And what we do there is that these are the molecules which are in motion randomly, and we say that if I take a surface there and say, well, how many molecules are hitting it, say if it is a solid surface, this molecule moved, hit it, bounced off. Let's assume it is perfectly elastic collision. Another molecule comes from there, hits it, bounces off. Another comes from there, bounces off. With each one of these, there is a change of momentum. And so we do not talk about how much was, as far as the molecule goes, its momentum changed because its velocity vector has changed. But what happened to this surface? It experienced a force. And so we take a largish enough surface, that means this dimension is big enough that there are millions of molecules hitting it. And then we take a two-dimensional thing, again on the same side, and then we say how many molecules are hitting it and bouncing off. And from there, we do the momentum change analysis and define pressure. So this is the thermodynamic definition of pressure. So we do not associate pressure with every molecule, but we do associate temperature with every molecule. And to get to the macroscopic property of pressure, we need to define a system big enough that there are a very large number of molecules in it, and that's how we can then define what is pressure. Okay, there's a question here which says, in most of the cases we are taking internal energy as function of temperature, then what about pressure effect? Okay, I have not even touched internal energy yet. Next module we will start talking about internal energy, and whether it depends on pressure or temperature will come in the module after that. Okay, so we can leave it for this time being right now. The next question is, what are the limitations of using hydrogen oxygen fuel cells in automobiles? Okay, so first the question is, the picture that I showed you was about a vehicle with a fuel cell in it, and what we have done in that, whether it was a okay, so that this device. Okay, I'm not too worried about the automobile, but I've taken the example of the bus. Whether you have an automobile powered by a petrol engine, a diesel engine, or a CNG engine, or a hybrid, which is partly by battery and partly by a combustion engine or by fuel cell, the fact is that the more cars you put on the road, the more you will see what you see on the roads, which is big traffic jams. That's all is going to happen. There is no running away from that reality. So let's look at the example of a bus. In this you can get 40-50 people going. It takes much less road space, much smaller carbon footprint even when you look at the diesel bus or the CNG bus, and of course there are many other benefits for your health if you take public transport. But coming back to the question, what are the limitations on this? Thermodynamics, as far as it goes, we would more be worried that can I get enough energy and enough power for driving this vehicle? Whether it is this, or whether it's a car, or whether it's a truck, or whether it is a crane, doesn't matter. So if I make a system which is very, very big and weighs say 10 tons, and you say, look, yes, I get the power, but as far as the transportation application goes, it's practically useless for us. So can you reduce the weight and reduce the size? So that is a practical thing. Thermodynamics still guides you what is possible and what is not possible, but it doesn't tell you exactly what will be the size of it. You need to go back to engineering and say, look, how can I make the size smaller and smaller, and yet we always be constrained by the thermodynamics. You cannot escape from that. And so if you can make it, that's what research has been going on for the last like 20 years. And finally you made a fuel cell, which as you see in this case, the fuel cell seems to be sitting on top of the bus. It has added that much height to this vehicle. In that you have also put the hydrogen cylinder. It probably takes oxygen from the air, and that's what you got on the top of the bus, and you added that much height to it. That is the art of engineering, which is the science of the possible. That's what is engineering. And so if once you get that and you say how much does it weigh, that's what weighs about 150 kilograms. So that's what it's about the weight of 2 or 3 people. So that's okay. So the bus is carrying 60 people, of that 2-3 are your dead weight there, we can live with it. So that's the next consideration, size and the weight, and then on one charging, how many kilometers will this vehicle go? So then you decide, well, how much hydrogen do I need to store in it? If it consumes hydrogen so fast that after every 100 kilometers I need to recharge it, it's not a very nice thing to have. And that's the reason why the hydrogen powered combustion engine is not a very great thing, but hydrogen based fuel cell has a big advantage over that. So saying that I can burn hydrogen inside an internal combustion engine, nice to do project, but practically it's practically useless. So that's the other thing that you get as a benefit here. So, and where do you locate it? The automobile that happened, we are able to pack all of that fuel cell and the hydrogen either in the trunk or in the front hood, and then we are able to get the electricity. The next part of possibility of making it was power electronics, by which you can convert that DC supply into something else, control it, and then drive an electric motor which powers the vehicle. So there you need to do work on electrical engineering, devices, machines, and make the control system possible. So those are the challenges that decide how and when and if these will become finally commercial reality. Fuel cells have several technical problems and challenges still. I won't call it a problem, it's a negative connotation. You can take it as a challenge. How do I make it? How do I keep it clean? How do I give it clean fuel? All of that is there. And the biggest thing that you have to convince everybody in the world is that if I put a hydrogen cylinder on a vehicle or in a car, is it safe? And you need to look at all types of possibilities that can happen for this vehicle and say, look, if this gets into an accident, then what happens? If this pipe breaks, then what happens? If the fuel cell cracks, then what happens? All of that goes in to make a technology successful. Okay, so that was the fuel cell question. What is the significance of entropy in the great circle of sciences? Okay, we'll talk a lot about entropy in the next module. Then the second law comes in and we'll have a lot to talk about it. Where will the application of the unit torr be used? Okay, so the question is torr is the unit of pressure. And people use it where you are always dealing with vacuum, very large vacuums, where millimeters of mercury, millimeters of water are no use, but you have vacuum much smaller than that, then we use the unit. And any device in which you have made a vacuum, that's what you would do. Okay, so for example, if you are doing material processing and you need a very clean environment, then you say that I'll measure the pressure of that vessel in torr. So it's purely a convenience thing. Using a bar or a Pascal or a megapascal is fine, but every time you tell somebody what the pressure is, you'll have to say, no, it is this much into 10 to the power 4 Pascal or 10 to the power 6 Pascal. That doesn't help in communication. So we use the unit of torr. How density and humidity are related to temperature? There is a question here. Okay, I am not going to pick it up right now. We'll come back to it when we look at the properties of a substance, because we have not yet considered what is the mixture and how do I get the properties of a pure substance. When we look at that, then we will look at this issue. So I'll keep that in mind. There's a question using microscopic approach of thermodynamics, how do we define temperature? I just answered that. Okay. If the temperature of atmosphere is constant, then why we face problems of global warming? Okay, so here's the interesting question. So when we talked about temperature of the atmosphere, what we are saying is that yes, for all practical purposes, we are saying that this is constant. It is not even constant, but what it is, when I say this is some sort of an average temperature at many locations over a long period of time. That is the average temperature of the atmosphere. So it is not at a particular location or anything like that. But when we talk of global warming, what we are saying is that, okay, I will look at the average temperature of the atmosphere, not at the temperature in this room or somewhere else, and look at this and how it has changed with time. And what we now have evidence for is that the average temperature of the atmosphere has increased by about between 0.5 and 0.7 degrees Celsius. And predictions are that in the next 20 years, this increase, so this is 1 degree Celsius. And what is the base? The base is pre-1850 average temperature. Because that is when the Industrial Revolution began, and that was the first time we started exploiting coal, first in a very big way, and then early 1920s we started exploiting oil and gas, and that is what started adding permanent CO2 to the atmosphere. So as long as you are only burning coal, the rate of addition of carbon dioxide to the atmosphere was relatively slow. Once oil came along, it spiked up and started increasing relatively fast. So this temperature increase which is happening and is going to happen, we think that this is small. And by engineering things that yes, a half degree change, it may not be very significant, but then please remember that even body temperature and my body temperature, when we have fever, our temperature of the body goes up only by half or 1 degree Celsius, and that's bad enough. 2 degrees Celsius increase in our body temperature and we are pretty sick. We get big fever. So it is not a small thing. The relative of what is small and what is large is relative to something else. What is this relative to is what it does to the overall energy balance of the atmosphere. And what are its implications? If the implications were not there, we say, look, forget about it, let it happen, no big deal. But then when you say that the sea level is rising, that the Arctic cap is melting, Himalayan glaciers are melting, extremes of climates have gone up, more frequent droughts, more randomly, more intense, more frequent floods, more randomly, more intense, more frequent cyclones, more frequent hurricanes. When we get evidence of all of this, we can still say, look, I can't be bothered. It has to happen, it's happened, I'm living a nice life, everything is okay with me, what's the big deal? Well, the thing is, it may not affect some people, but it will definitely affect a lot of people. For instance, sea level rise will affect 70% of the population of the world. And if your house is going to get submerged, what do? You go to somebody else's place, and that person doesn't like it, and you have a problem. If droughts and floods become common, your food is an issue. You have a big problem with food. Where will you get the food from? Plus, there is the damage that things do, like in the Himalayas, you have GLOF, Global Glacial Lake Outburst Flood, which is what happened at the Kedarnath Shrine a few years back. That's going to become more frequent. So that is what is got to be worrying us, and not whether this is half degree, 1 degree, or 0.75 degree. It is these implications, which is why that small change in the average Earth's temperature should be a cause for all of us to worry about. Okay? How difficult will it be to analyze a simple system with microscopic approach? Okay, I will give you an example from what research people are doing. Here's an example that we know that a particular material, say aluminium, has all its atoms arranged in a particular way. Okay, so in a 3D matrix, so this is all the atoms. And I say, I want you to calculate and tell me from microscopic approach what is the specific heat of aluminium. All the data we have is measured. Or we say, well, tell me what is the electrical conductivity of aluminium. Then say, okay, I know that in the microscopic approach what each of these atoms is doing, how they are connected to one another. I can write an equation for finding out what is the motion of this, this. I will simulate write the mathematics and run the computer code to do all that calculation. So you need some sort of at least a small mini supercomputer, a few days to work on it, and it will give you the answer. And it will tell you that specific heat of aluminium is this much and the thermal conductivity of aluminium is this much. That's the type of computing effort it takes to do a very simple calculation, which is a calculation of this thing. Or if you want to say that if I increase the temperature of these by 5 degrees Celsius, what will be the temperature change in the next 100 atoms? It will take that much time to do that calculation. We don't have that much luxury at the engineering level, but yes, if you are looking at very small levels and trying to answer these questions, that's what people do. So there are people looking at these questions and trying to answer this. Okay, let's take a second question of a chemical reaction. Is a molecule, say of butane, C4H10, your LPG gas, and another molecule of air, say oxygen. And like this, there are many oxygen molecules roaming around, and there are many of butane. And we want to calculate what is the rate at which the reaction will take place and how much energy will be given up. We have from school days knowledge that, okay, if there's complete burning taking place and the products come back to the ambient temperature, then so much energy is given out, and that's what we have learned as, say, a calorific value, and we got numbers on that. That's all done at the macroscopic level. But when you do it at the microscopic level, we can theoretically say, look, I'll simulate each and every molecule the way it is moving. I'll simulate the collision of two of them and see whether there will be some reaction. If so, what reaction will it be there? So what happens is that when two molecules hit each other, there is a probability of a reaction. So they will hit. So that means C4H10, one molecule has come. It had hit one O2 molecule, and it does not straight away become the reactants. It may become something like C4H10O plus O. Because probability that three molecules will hit at the same time is practically zero. All reactions will happen only when two molecules hit each other. Then this will hit something else. This will hit something else. Like that, there may be several hundred such reactions taking place, and finally we get CO2 plus whatever is the number of H2O that is there. 4CO2 and 5H2O. So here you get 4 plus 5, 9 molecules. We started off with 2 molecules, and every hitting is a 2 molecule process. So we can calculate all of this. Researchers in combustion and pollution do make such calculations, and from here we do get a lot of valuable insight into what is happening, but then we try to make it in a usable form that a designer of a combustor or a burner can use that knowledge. But it takes a supercomputer several days of a calculation to give the answer for this. So yes, microscopic approach is possible. It is done, but it's very time intensive, resource intensive, and as an engineering thing, it doesn't help us too much. Please give us an example of heat transfer from sink to source. Okay, I just gave that example, but I'll repeat it now. If I have energy transfer from sink to source, it will not happen by itself. Okay, so here there is a sink. Here there is a source. And this is at a higher temperature. This is at a lower temperature. If I just put a metal rod between them or any material between them, there will be heat transfer happening. We know that. Now if I want to make the opposite happen, what do I do? This can exchange heat only with a system whose temperature here is greater than TH. So that the system temperature at this point has to be, this is TL, is more than, is less than TL. That means the temperature here has to be less than this temperature. Then heat will come here. Then this substance is now already at a lower temperature, it cannot give its heat there. If we throw it into this at the end of it, it cannot do it a second time then. But if I want to do it on a continuous basis, we then have to put it to a compressor. Its temperature goes up, or you can heat it and raise its temperature. But to make it move, you still need a pump or a compressor. So you do something to it in this, where its temperature has now gone up. So when this is moving here, here the system has a temperature which is more than the source temperature TH, and now heat transfer is possible over here. Then we do something else and bring it back here. And that's the idea of what we may call a heat pump. Its job is to take energy from a low temperature to a high temperature, and it is exactly the reverse of a refrigerator. So one can argue that in winter, if I consume a certain amount of electricity to keep my room warm, then if I use the air conditioner in reverse, with the same amount of electricity, I can make the room even warmer. That is possible. These days you are now beginning to see those type of devices being marketed, where they say that this is in summer you can use it as an air conditioner, and in winter you do switch a few knobs here and there, and it will act like a heat pump, and you can use it as a heater in winter. So those devices are now there in the market. Okay, so that is there. Does at high temperature H2O2 fuel cell may have a chance of explosion? Okay, there's a question that if the hydrogen oxygen fuel cell is run at a high temperature, is there a probability of an explosion? So mostly the hydrogen oxygen fuel cells are being run at low temperatures. There are some which are run at high temperatures, but then you have to design it so that first it doesn't leak. If you are able to do thermal management of that, and yes, there is always a remote chance that it can explode. Much like if you ask the question, traveling in an aeroplane, is it possible that the engine will catch fire? And yes, there is a finite probability the engine could catch fire. But then that is what engineering is about, and we have to anticipate it, try to see as much as possible, and yet there would still be an accident, and we learn from it, and the next generation of that machine becomes more safe. And that's why aeroplanes, aero engines, cars today are so much more safer than what they were earlier. Okay, so that is there. Then get the next question. What is entropy and how it is related to energy? Okay, this is the question for our next module. I will definitely come back to that there. It will get covered, don't worry. In an isolated system, if there is friction, then the heat loss due to friction cannot escape. So can that be counted as reversible process though there is friction? Well, the answer is whenever there is friction, and you haven't said where is the friction, but if there is friction between two surfaces, then as the relative motion takes place, it generated heat. Now if you want to reverse it, it cannot happen by heating it up again. So it will always remain irreversible. So whether the system is isolated in itself or not. So the example I gave the stirring yesterday, I think, that if a liquid in a glass has been stirred, it has got energy, but due to friction that energy gets dissipated. Even though the system was isolated, what will happen is that energy by dissipation remains in the system itself. And that is an irreversible process. We cannot expect that by heating that liquid, that it can go back into motion. That's not going to happen. Okay, next is, why specific heat at constant pressure is greater than specific heat at constant volume? Okay, for this question, you'll have to wait till the third module. Then we will pick up this answer here. Okay.